Okay, in the previous experiment, we tried to talk about substitution reaction as one of the reactions in organic chemistry, and there we tried to see the two types of substitution reaction, the SN1 and the SN2, because these two reactions differ the way they start, and because of that their rate equation or their chemical reaction, the rate of their chemical reaction differs in such a way that in case of SN2 reaction, the reaction starts by the involvement of both the substrate and the nucleophile, whereas in the case of SN1 reaction, the reaction starts by by only the transformation of the substrate into an intermediate called carbocation without the involvement of the nucleophile. So the rate of the reaction for that SN1 is determined only by the substrate, whereas the rate of reaction for the SN2 is determined by both the substrate and the nucleophile. And today we're going to see the rate of reaction for SN1 reaction with experimental example. So this is a typical SN1 reaction because tertbutyl chloride is a highly substitute substrate, and you have the water as a nucleophile, which is a good nucleophile, and that makes it a substitution reaction. Beyond, however, here, in addition to this feature of reaction, you see that water is a solvent and is also used here as a nucleophile. So such reactions where the solvent acts as a nucleophile are called solvolysis type of reaction, and this reaction specifically is called hydrolysis because the nucleophile is water. Of course, in some other reactions where alcohol is used as a nucleophile, the reaction is called alcoholysis. Well, so if you try to look the mechanism, this reaction is substitution reaction because the leaving group or the chlorine is substituted by the OH, which comes from the water molecule, and because the water here is also a solvent, that makes it nucleophilic solvolysis reaction, a solvolysis nucleophilic substitution reaction. So here, the first step of the reaction is where the tertbutyl chloride converts to a carbocation intermediate, and because it's the first step, it's a rate determining step of the reaction. When we write the rate equation for this one, it will be rate constant times concentration of the substrate. And then reactions where their rate equation is determined by one substrate or one reactant are called unimolecular reactions. So obviously that the rate equation of SN1 reaction is determined by the concentration of tertbutyl chloride. That's why we can write the rate like this. So rate equation such as K rate equals to K times concentration of A for one reactant A are called first order reaction, which in other words means the SN1 reaction is also a first order reaction. So to determine the rate equation experimentally, we have to use this rate equation, and the rate equation for this SN1 is equals to rate constant times concentration of the tertbutyl chloride, and rate, in other words, is defined as the rate of disappearance of the reactant and formation of the product, and that's written as D into concentration of the reactant at time t divided by change in T. Sometimes you see the rate, the disappearance as delta to mean change in concentration over change in time over the period of time. So for our case, the equation 1 will be simply the rate equation for the transformation of tertbutyl chloride into tertbutanol, and because this is rate equation that differs over time, we can assume that at time t, concentration of the tertbutyl chloride was like 100%, like full, okay, because it's not yet consumed. So if we insert this, if we write this concept, it will simply be the right hand side of the formula will not be changed because it's being disappeared. However, the right side of the equation can be K1 into concentration of C0, where C means the concentration of the tertbutyl chloride. And so we can rearrange this equation by multiplying both sides of the equation by T over C0, and then we will have concentration at time t over concentration at time 0 equals to rate constant times t. If we integrate this, we can have ln concentration of because when you integrate, what you'll get is ln concentration of the tertbutyl chloride at time t as t goes from 0 to t equals to minus kt, or kt as t goes from 0 to t time t, which this simply means minus ln natural logarithm of concentration of the reactant at time t divided concentration of the reactant at time 0, or at the initial time. This is simply if we just because ln a by b means ln a plus b, right? So where ln a by b means ln a minus b, and if you write in that form, you will have ln concentration at time t minus ln at concentration at time 0 equals to K1 times t. If you rearrange this, you will have ln at concentration of times t equals to minus kt plus ln at concentration of time 0, where this initial concentration transfers the equal sign. This is simply a form of the linear equation y equals to mx plus b, where y is the y-axis, x is the x-axis, m, which is the rate constant. Here is the slope, where x is the time of the reaction and b is the initial concentration. However, we can also convert these natural logarithms into logarithmic function by simply substituting the ln by 2.303 log form, where ln x simply means 2.303 log x. Having this second equation, we can then try to put our reaction parameters into this equation. So the thing is, when tert-butyl disappears, at the same rate hydrogen chloride forms, which means we can determine the concentration of tert-butyl chloride by monitoring the concentration of hydrogen chloride. And at the end of the reaction, we will not have any concentration of the tert-butyl chloride, but we will have full concentration of, we will have 100% of hydrogen chloride and no any tert-butyl chloride. So let's say the final time for this reaction is T, which is infinity, because we don't know what time that will be. So at this time, all the tert-butyl chloride is consumed. We do have no any tert-butyl chloride, but we have 100% or full of hydrogen chloride. So, which means, because we said the rate at which tert-butyl is consumed is equal to the rate at which the hydrogen chloride is formed, we can simply relate the initial concentration of tert-butyl chloride equals to the final concentration of the hydrogen chloride. So at any time t, concentration of hydrogen chloride will equal to the final concentration minus the concentration at time t. This can be rearranged into just by transferring the C0, or by transferring the concentration of hydrogen chloride at time t. You can have concentration at time t equals to final concentration minus concentration of hydrogen chloride at time t, which is again can be rearranged into, because we said the C0, the initial concentration, is equals to concentration, the final concentration of hydrogen chloride, and we can have concentration of concentration at time t equals to final concentration minus concentration of hydrogen chloride at a certain time. So when we substitute this to our second equation, we can then find the third equation just like this. And so what we are trying to determine here is the concentration of tert-butyl chloride. So the concentration of hydrogen chloride is determined by monitoring any of the concentration of the reactants participated in the reaction. In our case, all the things we add to the stock solution. So simply this means the concentration of and because in the stock solution, this is simply related to typical titration reaction, actually, where we use the concentration of base, our titrant, to determine the concentration of the acid consumed. So similarly here in the stock solution, we say the concentration of hydrogen chloride is proportional to the concentration, to any concentration, to any of the concentration of the reactants in the stock solution. And because we have the base in the stock solution, which means concentration of the hydrogen chloride is proportional to concentration of the base. So simply we can replace the concentration of the hydrogen chloride in equation 3 by concentration of, or by the amount of sodium hydroxide, and we can have this equation. If you divided both sides of the equation by 2.303, then we will have log amount of the final amount of sodium hydroxide minus the amount of sodium hydroxide at time t divided the final amount of sodium hydroxide in the reaction is equal to rate constant times t divided 2.303, which will be our final equation. Well, so in the experiment, we'll first prepare our titrant solution, which is sodium hydroxide, which will be about 0.04 normality. You can simply prepare this by adding 8 grams of sodium hydroxide pellets into 5,000 milliliters of distilled water. And then next is the stock solution. So the stock solution, for sure, because we're talking about SN1 reaction, and you can try to understand that the stock solution is simply the major reaction we have, and the reaction, the SN1 reaction in general. So we will prepare that stock solution by adding by adding equal portions of water and 2 propanol, which are the solvents, into 1.2 milliliter of tertibutyl chloride, which is our substrate in the volumetric flask. And then this is the stock solution, and we will keep this solution to undergo the reaction because we have added the solvent and the substrate and what we expect is the reaction to happen. We will keep this reaction to go for about 75 minutes. And meanwhile, because our completed reaction is where hydrogen chloride and tertibutanol is formed, we can simply form that reaction by adding excess water into the stock solution. To do this, you can simply take 10 milliliters of the stock solution from step 2 in 125 milliliter Erlenmeyer flask and add 10 milliliter of water into it. So this will be the final reaction. So, but because we have to monitor the concentration of the reactant is consumed and produced, we have to monitor the reaction, the overall reaction at different times. So once the stock solution reaches 10 minutes, we have to take 10 milliliters from that stock solution and then add 10 milliliters of acetone to it and 1 to 2 drops of bromothymol blue, which is simply our indicator. And we're adding acetone. Imagine acetone is a polar aprotic solvent that's not favored by SN1 reaction. We're adding it here to stop the reaction, and we can then titrate the solution by our titrant sodium hydroxide until we find a pale green color in the Erlenmeyer flask. Most of the time this color might not be that strong, and it's better if you do your experiment in a white table, or you can put a paper at the bottom of the Erlenmeyer flask. And then you can record the, so once you see the end point result, you can record the amount of sodium hydroxide used for until the end point. So the experiment is simply to do this at different times, and you will do this when our stock solution from step 2 reaches 20 minutes, and then you do the same at 35, 50, and 75 minutes. So the 75 minutes is at time t, the final time, where all the tert-butyl chloride is consumed and hydrogen chloride is fully formed. Remember that we have prepared this solution in before to make ready the complete reaction by adding more 10 milliliter more of water, and we can then titrate that to see the final volume of the base required to for the complete reaction, because that will help us to monitor the reaction. So the process is the same. You add your indicator into the previously prepared stock solution, the infinity stock solution, with additional 10 milliliters of water, and then you titrate it with sodium hydroxide. So likewise, you'll have the amount of sodium hydroxide for this reaction, and you will have the amount of sodium hydroxide for each of the titration you undergo at different times, and you create such a table in your lab book or in an Excel. So when you draw a graph by substituting these values, as you can see, you have concentration of the amount of sodium hydroxide used, the final volume, minus the amount of sodium hydroxide used in each of the times, divided by the final amount of sodium hydroxide used. You can calculate, you can draw the graph. You can draw the graph because you have the time too. Then you can calculate the y-axis, because you have all these axes here, because this is so yeah, you have the time here. What you do is you just calculate this equation to get the y-axis, right? So at the end of the process, you will have such a linear graph, and because the Excel itself calculates the R square for you, and R squares near to 1 are good linear fit, whereas R square far less than 1 are bad linear fits, and then you're done, which means you're able to see the way the reactants are consumed and products are produced, and then you do appreciate the way that we can determine the volume or the amount of the reactant used by monitoring the amount of the product formed. Well, that's it for me regarding the experiment. And as usual, if you have unclarity in in any of the lectures, in this lecture or in my previous lectures, you're welcome to ask me through by writing your questions in the YouTube channel. Thank you for your time.